Welcome class to Advanced Aircraft Systems. I'm your instructor, Tom Mahoney, and today we're going to give you a lecture on how a jet engine works. That's what this class is about. The jet engine we're going to be looking at today is typically going to be the CRJ 700 jet engine. It's a fairly typical jet engine for today's standards. This is where we're going to get started with our lectures for this semester. So let's get going. And here we are into the PowerPoint module I prepared. Now, these modules are based off of the AeroSim program that you will go back and continue to review. The AeroSim modules treat that like it's your textbook, treat my PowerPoint programs like it's a class lecture. And that way you can progress more normally through the class. So how does a jet engine work? Well, it's pretty simple. It's suck, squeeze, burn, and blow. So if you're talking to somebody who's on the street, doesn't understand this stuff that well, keep it simple. And for now, suck, squeeze, burn, and blow. What we'll be talking about in this class is high bypass jet engines. This is what most commercial airliners are using today. These jet engines aren't pure jets. Most of the air that is used to create thrust is what we call bypass air, and a percentage of it is what we call core air, which is actually the working air. So we have another word for this. It's called fan jets. They're just high bypass jet engines. So let's get used to the basic parts. Talk about the N1 rotor. I call it the N1 fan, so you'll hear me refer to the N1 rotor as the N1 fan. It's located at the intake end of the engine and is the fan section. Normally includes a forward compressor. So let's annotate some of this stuff here if we can. Get my computer set up. So this is your fan right here. I call it the N1 fan. And the N1 fan is also referred to as the N1 rotor. Sometimes behind the N1 fan, you will have a compressor section called the N1 compressor. Doesn't show it too much in detail here, but a lot of jet engines will have an N1 compressor attached directly to the N1 fan. Okay. Now you go to the N2 rotor, which I refer to as the N2 compressor. That is in this section right here. And this is the part that actually squeezes the air down just prior to combustion. So this is kind of like in a piston engine, this would be your piston that squeezes the air down and gives it some real pop when it does explode the fuel once the fuel is injected into the compressed air. All right. Continuing with basic parts, we have the low pressure turbine, I refer to as the N1 turbine. It is located right here. And the N1 turbine is what turns the fan up in the front. And you'll have a shaft that moves all the way forward. This is can be pretty much, just think of it as a solid shaft connecting the low pressure turbine and the N1 rotor together so that when the turbine is spinning, turning, it will rotate the fan. More basic parts, the high pressure turbine is the N2 turbine. The N2 turbine is located right here. We've talked about that. and it's the high pressure turbine. And then we also have the combustion chamber right here. And right behind the combustion chamber is our high pressure turbine, or as I refer to, the N2 turbine. So we have the N2 compressor, the N2 turbine, and between the two, we have the burner can or the combustion chamber. So those are your basic parts. Let's recap real quick. Left to right in our schematic, we have the N1 fan, often with a compressor attached, and we call it the would call that the N2 compressor. Correction, the N1 compressor. Then we would have right behind it the N2 rotor, or what I like to call the N2 compressor. Then behind the N2 compressor, we have the combustion chamber, or I commonly refer to it as the burner can. And behind that, we have the N2 turbine. That's the high pressure turbine. And then we have the N1 turbine connected all the way to the front to the N1 fan. Now let's talk about the difference between core air and bypass air. So bypass air is the air that circulates around the outer core of the engine. It travels along that route. Here's some more down here. And this happens all the way back to here. We call this bypass air. Let's draw that on down here. So there's your bypass air. It's the non-working air in terms of making the engine run, but that is where the bulk of the thrust comes for a jet engine on a high bypass engine. The core air is the air that comes down through the center of that big old jet engine. And this here is what the core is. So it's all the working parts of the jet engine. It's the air that makes all of the components of the engine turn, which is what helps provide for bypass air. So about 80% is bypass on this engine, and 20% of the thrust is core air. So let's take a look at the bypass air a little more thoroughly. The bypass air, as we indicated, is around the outside of the core of the engine, comes all the way back to the aft of the engine, all the way around the engine, and it produces about 80% of the engine's thrust on the CRJ 700. It can be as low as high as 90% of the thrust, depending on the efficiency of the engine. Now, bypass air does something else that's rather interesting. Bypass air comes all the way around here like this. I'll just draw it this way. And produces all that thrust, but it does something else. It provides an air barrier right through here that muffles the sound of the air coming out the back of the engine, out through the tailpipe, that as a result of core air. So the core air is the noisy air. The bypass air is typically the quiet air, and it can muffle the noise of that core air as the core air exits the aft portion or the tailpipe of the engine. So let's put all the parts together. We've got suck, squeeze, burn, and blow. Again, we've talked about this being the simple concept. So let's see how this all works when we put it together. The suck portion, of course, is the front of the engine, where the air is coming into the front of the engine. The fan in the front is sucking air in, and then it bypasses some air around the outside, and then takes some air down through the center. And that's wonderful. That's the working air. That's what makes all the components in the jet engine rotate. And once you get that suck going, the engine almost wants to continue to run as long as there's fuel. The squeeze part of the engine is this part. And I'm going to go ahead and get my pin back up here. This is the squeeze part. What do we call that? We call that the compressor section N2, the N2 compressor. Now, the N2 compressor is made up of a series of rotors and stators. These things right here are rotors. Now, you can remember they're rotors because they're the part that actually spin. The stators are little fins in between the rotors that redirect the air to the next rotor so that the rotor can grab the air more efficiently and keep pushing it rearward. And as it pushes it rearward, the space that it gets pushed into gets less and less, so the air gets compressed more and more until it gets to the aft end of the compressor right here, and it builds up what we call a pressure wall. Okay, so keep that in mind. We have a pressure wall at the aft end of the compressor or N2 compressor. What is that? What are they made up of? What's the compressor made up of? Of course, it's made up of rotors, rotor sections, and stator sections. Creates the whole thing is now called the compressor. Now we get to the burn portion. We talked about this right here. That's the burner can right in that area. So the fuel gets injected into this area. And there are some igniters around the outside perimeter of the burner can. I guess the fuel may get injected in here. Okay. As the fuel gets into the burner can, igniters around the outside area of the burner can ignite the fuel. That fuel air mixture created by the compressed air coming into the burner can lights off and expands rapidly. Now, the question is, why doesn't it move forward as opposed to moving backwards? Because as we mentioned, we have this pressure bulkhead here and no pressure bulkhead at the aft. So the path that the expanding air wants to travel is the path of least resistance, which will take it rearward over the and past the turbines, the N2 turbine and the N1 turbine. Once it passes over those N1 turbines, we get another bit of action going on. And that's the blow. So it blows past those turbines. Of course, if you blow air past the turbine, what's going to happen? Those turbines are going to start to rotate. If they're designed properly, they will rotate at a rather excessive amount of speed. Now, since the N1 is connected by a shaft to the fan, likewise, the N2 turbine is connected to the N2 compressor by a shaft. So if the N2 is starting to rotate, the N2 turbine is starting to rotate, it will continue to rotate the N2 compressor. As the air passes over the N1 turbines, it will rotate and in turn rotate the fan. And once you get that happening, it's pretty easy to keep an engine running. As long as there's fuel being added to the burner can and the air mixture coming from the compressor will mix with that air or that fuel. And if the fuel's already burning, it will continue to burn. At that point in time, you don't even need to have the igniters functioning. So in summary, air is sucked into the front of the engine by the N1 fan. Some intake air passes into the core of the engine where it is compressed by multiple stage compressor blades. At the back end of the compressor, a pressure wall is formed ahead of the combustion chamber. As air enters the combustion chamber, fuel is also added, and you have an air-fuel mixture that is burned. The expanding gases move rearward, of course, because it can't move forward because of the pressure bulkhead, and passes over the N2 and then N1 turbines. This causes the turbines to rotate. Then in turn causes the N1 fan to rotate, suck more air in, and then the N2 is also separately turning as a result of the N2 turbines turning, and the cycle continues, and the expanding air exits the back, and that is what we call the core air, and that core air produces about 20% of the thrust, and the bypass air produces about 80% of the thrust. That is on the CRJ 700 engines. That's as simple as it works. Don't make it more complicated than that. Let's talk about the igniters that are actually like little spark plugs that lit the fuel off to begin with when we were starting the engines. Of course, we don't need the igniters on all the time once the engines are running. However, there are times we would like to have the igniters running just to make sure that the flame continues to burn inside the combustion chamber or the burner can. Obviously, we're going to have them being ignited during engine starts or restarts, because if the engine is not running, we're not generating any air fuel mixture, so therefore nothing can burn. So we got to get that stuff rotating first and then burning, and we do it with the igniters. If we run into icing conditions, we'd like to have the igniters running during icing conditions, just so we can make sure that for some reason the burner can is not going to flame out. If we're on contaminated runways, what do we mean by contaminated runways? We're talking about a lot of water, a lot of slush, that type of stuff that could spray up into the engines, that could eventually make its way back into the burner can, and possibly again put the fire out. If we're in moderate or greater turbulence, we want the igniters on, and of course in heavy rain, we would obviously want the igniters on. And in some cases, they will come on automatically. In other cases, we need to make sure we flip the switches on for the igniters and manually keep them igniting. So let's move on to FADEC. I don't know how many of you have heard of FADEC, but it's called Full Authority Digital Engine Control. This was a great invention when it came out. It's how the engines are operated. This thing controls the operation. It's a computer is what it is. And it tells the engine how much fuel it should be taking in, how much air it should be taking in, what the RPM should be, etc. So it's full authority digital engine control. The FADEC is the primary computer that controls the engine operations. Normally, there are two FADECs for computers for each engine. Each FADEC operates independently from the other and only one at a time. It only takes one FADEC to operate the engine. So now we have a backup in case we lose one FADEC. The other FADEC continues to step up and then takes over the operations. Now these FADEC computers actually switch positions as to which one's operating every time you shut down an engine and start it back up. If FADEC 1 had been running before, it shuts down, FADEC 2 comes online, and now it's controlling the engines. If, of course, you have an engine failure or a FADEC failure, the non-operating FADEC would jump in and then begin to operate in place of the failed FADEC. So what does the FADEC actually do? This is what it does. It's the brains of the engine. You are telling the FADEC what to tell the engine. You do that through the use of the thrust levers. The FADEC is the brains You are just the mechanism that tells the brain what to do. How do you do it? You push the levers forward and aft, and the FADEC will interpret the position of those levers and then tell the engine how much thrust to put out, when to start, a lot of different things it does. So let's take a look at what it does specifically. It sequences start valves, ignition, and fuel flow during engine start. In the old days, if you were starting a DC-9 engine, you were the FADEC. You had to make sure these valves were open, the ignition was on, the fuel was flowing before you actually started the engine. Well, today, FADEC will take care of that, all of that for you. It's a great deal. It's a great invention. Love it. Started using it about halfway through my career, actually a little more than halfway through, and don't ever want to go back to the old stuff. It gives you overheat protection during engine starts, N1 and 2 overspeed protection. It's a calculation of maximum thrust values and adjusting minimum idle speed, reverse thrust sequencing. So when you pull the reversers out after landing, it sets up how those thrust reversers are going to operate when thrust reverse is actually applied, and it does it automatically through automatic sequencing. And then it also recognizes when you have an engine fault and can give you that detection ability. And then it displays those engine indications and alerts on your ICAS pages up in your flight deck. Thrust is controlled by the fuel management unit. We call that the FMU. When you position your thrust levers at a particular point on the console, there are no cables that go back to the carburetor on the engine, so to speak. They've got some rheostats basically that measure or detect the position of your thrust levers, that sends that signal to the FADEC. The FADEC interprets that position, and then it sends a signal to the fuel management unit, and that fuel management unit then dictates how much fuel goes into the engine burner can, basically, so that you can produce the appropriate amount of thrust that was detected by the position of the thrust levers, and that input is done by the pilots. So everything's computer driven, works good, works a long time. Let's talk about the accessory gearbox on these engines. You have to be able to translate the jet engine power into other types of power that are used throughout the aircraft. So this is how they do it. They do it with an accessory gearbox. The accessory gearbox is this right here. It is attached to the N2 shaft right in this area. So it's geared. So when the N2 shaft is spinning, the gearbox is spinning, and then the gearbox rotates and operates certain pumps, generators, that kind of stuff in the aircraft. So what are they? There are things like the lubrication pumps, the hydraulic pumps, the fuel metering unit we just talked about, the integrated drive generator. So that's the generator on the engine. Those are the big generators. It operates what we call an air turbine starter. That's the starter that is engaged through air pressure that makes the engines rotate for starting purposes. And we have an integrated oil reservoir, a FADEC alternator, which is the alternators that actually operate the FADEC independently of the engine-driven generator. So the FADECs, they're so important. They have their own dedicated alternators. And if the alternators fail, then or the generators fail in the engines, we still have our FADEC alternator providing us information about that engine. So when the engines are operated, excessive air is ducted away from the engines in the form of bleed air. So this is what bleed air is. It's excess air siphoned off the engines that we use to run the pneumatic system. These items right here, these tubes coming off this engine, are what we call bleed air ducting. So they actually dip into the engine, mostly at the compressor, the into compressor section, and because that's where all the compressed air is that we are able to use, we siphon that off and we use it for pneumatics. So what is bleed air? Bleed air is compressed air that is ducted off the into compressor. Low pressure bleed air comes from the forward section of the compressor. High pressure bleed air comes from the more aft sections of the compressor. In both cases, this air is very hot. As you recall, as it travels rearward through the into compressor, the air is compressed and becomes heated up. So here's our compressor right in this area. And this little item right here is what we call the location for the low bleed air pressure. And we have a high bleed air pressure takeoff. And that is where we siphon off the pressure from the uh, turbine, not the turbine, but the compressor. And that pressurized air would flow down this tube. And in some cases, we would use high pressure bleed air coming this way and joining again with the other air in the pneumatic cross sections, pneumatic tubing. Let's take a little closer look at what we mean by the bleed air, what it's used for. Modern jet engines use bleed air related to aircraft pneumatic systems. Specifically, it provides the following: pressurization to provide for breathable air. So we have to pressurize the cabin of the aircraft, and by pressurizing that air, we're able to compress it down to where we can actually inhale the oxygen contained in that air into our lungs. And then, of course, we use the same kind of pressurized air for controlling cabin air temperature, because remember, it's warm. We can mix that warm or hot air with cooler air, actually modulate the temperature of the air coming into the cabin. It's also used for ice protection. We can take and dump off some of that bleed air up into, for example, we can bring it up this direction, put it into the leading air wing ducts along here, use it for pressure heat. We can also take it and put it in front of the engine cowling, warm up those engine cowlings so we don't have any ice in those areas. And in the event that one engine is already running, we can siphon off air from, say, this engine and bring it all the way over to this engine, take it up and spin the air starter motor right here, which is attached to the N2 shaft, and it's mechanically attached. So if we take that bleed air over here, we can run that motor just like it was an air drill, and that'll get the engine started over here, at least get it rotating so we can get the engine started. We also have a couple other sources of bleed air. We have external bleed air. We can just plug a high pressure hose into the aircraft right here. Let's say this was a pressurized bottle and the aircraft was sitting on the ground. We could pump air directly into the pneumatic system, and that would not quite be called bleed air, but it is pressurized air. The other place we can get bleed air is from the APU, which is another jet engine. We use the APU to actually start the engines in most cases. It can provide bleed air because it's a jet engine, and it can also uh, run pressurized air throughout the pneumatic ducting. So that completes my lecture on engines. You need to go to your Aerosim modules now, get the full meal deal. You've paid for it. You need to use it. It's part of the class. It's going to give you much more detailed information than I can give you on my lecture. It does it in a very systematic way. The Aerosim program was put together by professionals, and these guys are computer techies, and they really know how to put a presentation together. Get into that module on engines in your Aerosim program, complete it, answer all those questions at the end of the modules. Don't forget, sync that when you get done, so I know you've done it, and I can give you credit on your grade sheet for having completed the engines. And then also, after you've done that, go into Hangar Talk, develop a question that you can put onto the Hangar Talk discussion board, see if you can stump some of your fellow classmates, and make sure you do it based on the rules. You cannot get on to Hangar Talk unless you place a question on it. You cannot see other people's questions until you place your own question, I should say. So until then, all I've got to say is I love my job. Glad to be here. Hope I can make a difference.